Okay, so hi everybody. Let me start by thanking the organizers for their invitation, for organizing this beautiful workshop, and for the opportunity to come and give a talk here. My name is Shlomi Reuveni. I'm from the School of Chemistry at Tel Aviv University. And today I would like to discuss the inspection paradox approach to stochastic resetting, which is an emerging field in statistical physics that was already mentioned during this workshop. And I will elaborate on this in my talk today, which will be focused on stochastic resetting. But I would like to focus on the connection between the inspection paradox and stochastic resetting. So I'm going to start with an introduction to the inspection paradox. And the person that you see here before you, this is William Feller, and he popularized the inspection paradox with a famous bus stop example that he gave in his book, famous book on probability theory. So we'll discuss this paradox. We'll see that it's not really a paradox, rather it is a surprising result. And then I will show you that there is an intimate connection, actually, between the inspection paradox and systems with stochastic resetting, and that, in fact, we can rederive and understand, shed light onto fundamental results that were obtained on systems with stochastic resetting by drawing insight from the inspection paradox and actually prove some things using minimal mathematical tools, really basic elementary mathematical tools, things that really took us as a community quite some hard labor to prove. You can show by appealing to the inspection paradox. So this is the plan, but before I start, I want to give credit where credit is due. This talk is based on a paper, The Inspection Paradox in Stochastic Resetting, that was published in a special issue of the Journal of Physics A, Stochastic Resetting Theory and Applications, in celebration of the 10th anniversary of diffusion with stochastic resetting, which is a paper by Martin and Satya that I will refer to multiple times during my talk. And hopefully, when I finish, you'll get the flavor, hopefully, of why are we celebrating. And if not, I'm hoping that by the time Martin finishes his talk, you'll see why. And there is really a lot to be excited about, in my view at least. Who did the work? Dr. Arnab Pal, who was a postdoc in the group, and now moved to start his own group at the Institute of Mathematical Sciences in Chennai. And Dr. Sarah Kostinsky, who was also a postdoc in the group, and will soon start her own group at NYU in the physics department. Here's a reference, and I think that now we're ready to go and discuss the inspection paradox. So I'm going to illustrate the inspection paradox with the same example that Feller used in order to illustrate it. And this is the bus stop example. So I want to think about a bus station, and I want to imagine, for simplicity, and we'll generalize this in a minute, that buses arrive to this station exactly every t units of time, okay? And then I'm a passenger, and I arrive to the station, and I'm interested in the following question: how much time do I need to wait until a bus comes and picks me up? This is I'll denote this time by T-res for time residual. This is the residual waiting time. And I want to know how much time will such passenger wait on average. So you can argue as follows: you come at some random time, so you're equally likely to land to the left or to the right of the midpoint of any interval that you land in. And then just by symmetry, because there's no bias, the time that you're going to wait is just half the size of the interval. On average, this is the mean residual waiting time. It's just half the size of this interval. And this is indeed the right result. Now, I want to think about what happens when you have fluctuations in this problem. So I want to imagine a situation where buses don't arrive deterministically, but rather there is some distribution of time between bus arrivals. And let's take this distribution to be exponential. So we consider a situation where these bus arrivals follow a Poisson process with a mean inter-arrival time that is just the mean of t. Okay? This is the random variable. I'm asking now the same question. I arrive at a random time, and I want to know on average, how much time am I going to wait until a bus comes and picks me up? So you can say, not a lot really changed. There is symmetry. If I land at some interval, I'm equally likely to land to the left or to the right of the midpoint. And so what I'm going to wait is just half the size of an average interval, because these intervals are t on average. So you can say this, but if you do, then you'll be wrong. This turns out to be the wrong answer to the question. The right answer is that you're going to come and you'll wait on average a time that is exactly the same as the mean waiting time or the mean interarrival time. So T-res in this case, where times between arrivals are exponential, is exactly the same as the mean waiting time. And you can say, okay, I understand this. I understand this. This is just because the exponential distribution is memoryless. So if you come at some time and you don't see a bus at the station, then you can forget about the past. The time going forward is also taken from an exponential distribution with the same mean. This is what I'm going to have to wait. And so it's clear that these means are the same. Still, if this is the first time you're seeing this, maybe you're moving in your chairs a little bit and you're saying, okay, how is this possible? Because some time has already elapsed and I'm basically waiting the same. But this is life. Now things get more interesting when you consider general times between bus arrivals. So what is the question again? Here the distribution was well specified. It's an exponential distribution. This is what I can. Now I want to go to general distributions, okay? So some general distribution, but with a given mean, a finite mean. And you could say, okay, what now is going to be the answer to this question? What is the mean waiting time, the mean of the residual waiting time? If there's any justice in the world, then it should probably be bounded between half the size of the interval and the entire size. But turns out that this is not the case. And in fact, there are situations, and I will show you in a minute, situations where you will arrive at the station and you're going to wait longer than the mean time between bus arrivals. And this time could be much, much longer, and I'll show exactly when. So this is the inspection paradox. How is this even possible to come after some time has elapsed? You expect to wait less, and in fact, you wait more. How is this possible? So to understand this, the crux of the matter is that what you actually have here is a strong sampling bias. And once you understand this sampling bias, you can understand the result and reconcile the paradox. So let's resolve the inspection paradox. So I'm thinking again about these buses, and they arrive, and there's an inter-arrival time T1, and then T2, and then T3, and so on and so forth, taken from some general distribution with a mean. And I want to compute the empirical average of this time, T-res, over a very long observation time, okay? So if you tell me that you landed at some specific interval I, then by symmetry, it's true. You're equally likely to land to the left or to the right of the midpoint of the interval, and what you're going to wait on average is just half the size of this interval. However, you need to multiply this by the probability that you really landed in this interval. And then sum over all the possible intervals. What is this probability? Well, if you come randomly in time, you're sampling time points at random, then this probability to land here is proportional to the size of the interval. And then to get a probability, you need to divide by the total observation time, basically the sum over all these intervals. Now you see that you become sensitive to Ti squared, basically to fluctuations in the inter-arrival time distribution. So you can take this expression, rearrange it a little bit, divide numerator and denominator by n, take the limit n goes to infinity, and get this result. The mean residual waiting time is just the second moment of the inter-arrival time distribution over twice the first moment, okay? And you can write this instead of in terms of the second moment, you can write this in terms of the variance or the standard deviation and the first moment, like that. And what will appear here is just the ratio between the standard deviation and the mean. This is the coefficient of variation of the distribution. It's a dimensionless measure for dispersion. And when you do that, you see that the mean residual waiting time is just half the size of the mean waiting time, or the mean interarrival time between bus arrivals, but you need to multiply this by 1 plus CV squared, okay? 1 plus the coefficient of variance squared, coefficient of variation squared. If there are no fluctuations, if sigma is 0, the standard deviation is 0, deterministic bus arrivals, this is 0, and you weigh just half the size of the interval. If you have an exponential distribution, the mean is equal to the standard deviation. This is 1, this is 2, the 2 kills the 2, and the mean residual is equal to the mean. However, in any case where for any interarrival time distribution where the standard deviation is larger than the mean, you're going to wait more than this mean time between bus arrivals if you come at a random point in time. And this happens because you're biased to sampling longer intervals, because you're sampling equally time points, not intervals, okay? So this is the resolution of this paradox, and now I want to move on and discuss another paradox, and after so we checked all the limits and we resolved the paradox. I want to discuss another paradox, and after I'll do that, I'll show you that the two are actually related. So they seem distinct, but they're the same. So now I want to talk about the resetting paradox, okay? Which is, again, not a paradox, but a surprising result. I want to think about what happens when you take a process, you stop it, and you start it anew from time to time. And for concreteness, let's first consider the simplest example possible. Let's think about motion with constant velocity. So you have a particle and you have a target, and the distance between the two is L, and at time 0, the particle will move towards the target at a constant velocity v. How much time does it take the particle to reach the target? This is the first passage time, just L over v, no fluctuations, nothing, very simple. Now I want to reset the motion of this particle with some rate r. What does it mean? It means that for every infinitesimal time interval delta t, there is a probability r times delta t that I will take the particle, wherever it is, place it back at the origin. So you could now have things like that. The particle starts moving, resetting occurs, you place it back, and you let it go again, and again, and again, and again, until it is able to hit the target for the first time uninterruptedly when you have no resetting. And I'm asking the same question. How much time will it take the particle to hit the target on average? Because now everything is stochastic. So without thinking a lot, you could say, okay, whatever it was before, now it has to be more than that. Why? Because the last trial in which the particle was able to reach the target, this took L over V units of time. But before that trial, maybe there was 1, 2, 3, 4, who knows how many trials in which you spent some time, resetting occurred, and you had to do it again. And these also need to be taken into the calculation of time. So the mean first passage time with resetting has to be more than the mean first passage time without resetting. And you could say, okay, it's clear, right? You take a process, you interrupt it by stopping it and starting it anew. All you can achieve by doing that is hinder the completion of the process. This is a very basic intuition that at least I had when I started working on these problems. The problem with this intuition is that it's wrong. It's completely wrong, and there are many, many, many counterexamples. One counterexample that resonated particularly well with the physics audience is the example of diffusion with stochastic resetting. So this is the paper by Martin and Satya, which de facto instigated a lot of work on these topics. Yeah. Yeah. Sorry? No, it cannot. It cannot. It cannot. Definitely not. I'm saying, but I'm saying that this is not a general feature. This we cannot generalize from this special example. Yeah. There are other examples which break this intuition. And yeah. And no. Okay. And we'll dive deeper. So one counterexample is this example of diffusion with stochastic resetting. You take a particle, you let it diffuse, and you reset it with a rate r to the place where it started. And now you want to put a target maybe here, and you want to ask, okay, when will the particle reach the origin or the target, and you could mistakenly think, what is resetting doing here? It's focusing the particle to its starting position, and so it will not explore space as effectively as a particle that is doing diffusion without resetting. And so here also, resetting will somehow hinder the first passage to the target, but in fact, it's not correct, and the exact opposite occurs. So now I want to say a few words on that. So basically, it's the same setting. You have a target, you have a particle, the distance is L, but this particle is now diffusing with some diffusion constant D. What happens without resetting? We know this, it's a classical problem. The first passage time distribution of a particle to a target in 1D is given by this formula. If you integrate over it, you discover that this is normalized to 1, which tells you that the particle will for sure hit the target in 1D. However, this first passage time distribution has a heavy tail, and it drops like 1 over t to the 3/2, and this means that the mean diverges. And so on average, you're going to have to wait an infinitely long time to see the particle hitting the target, which is one of the biggest surprises that you learn when you start learning about random walks. What happens when you introduce resetting? And this is one of the many results that appeared in this paper. Doesn't matter what you take for the resetting rate, the mean first passage time becomes finite. And so if you think about it for a second, you took a process that on average took an infinite amount of time to complete, and you made it complete in finite time, which is a huge improvement, just by stopping it and starting it anew. So you got a completely different result from the result that you get for ballistic motion. The question now is, okay, how can we understand this? Maybe in this case, but more generally, we want to think about the general case. I can apply resetting to any process with a start and a finish. Any first passage time process, I can think about it with resetting. So maybe I have a group of searchers that are looking for a target, but then bad weather or nightfall will force these searchers to go back to base, and then this is first passage under restart. You need to start all over again. Maybe you have a computer algorithm that scans stochastically a tree of possibilities, and maybe chance sent this algorithm down the wrong path and it missed the solution. Maybe you want to code then restart into your algorithm so as to give it a second chance of finding the problem. Maybe you have, and in fact, computer scientists do this all the time when they use stochastic computer algorithms. Sorry? Especially with Windows, yes. We all know it, that shutting down and starting over sometimes helps. Maybe you have a molecule and you prepare it at some excited state and it decays to a low energy state that is not the product that you were hoping to get. Then maybe perhaps by a laser pulse you can re-excite it, and now perhaps it will decay to the correct product, and so on and so forth. All these scenarios and many, many, many more fall under the context of first passage under restart. You have some starting point, you have a finish point. It actually doesn't have to be a point, it could be a region. You can have a distribution of starting conditions, doesn't matter, but there is some process that takes you from start to finish, some first passage process, and on top of that, you put resetting, and the million-dollar question is, what is the effect of resetting? In what situations will restart expedite completion? In what situations will it hinder completion? What exactly can we say about these kinds of things? So I want to say something about how we approach this. So we now have what people refer to as the renewal method. And the renewal method actually allows you to answer this question in a very general way. If you know how a process behaves without resetting, the renewal method allows you to say anything you want to say about the process with resetting. So, for example, in the context of first passage, if you want to know the mean first passage time of something under resetting, which I denote here by T sub r average, It turns out that this is just the mean of the minimum between r and t, when r is the resetting time and t is the first passage time, two random variables, and over the probability that t is smaller than r, the probability that first passage occurs before resetting. If you plug in a constant resetting rate, namely an exponential distribution for r, you can write this formula in terms of the Laplace transform of the first passage time distribution, very conveniently evaluated at r, and this is how it reads, 1 minus the Laplace transform over r times the Laplace transform. And now you can plug in any problem that you want and immediately get the mean first passage time, and you can do this for all the moments for the distribution. You can do this for steady states. You can do this for time evolution with resetting, everything you want to do. I will not discuss the renewal method in my talk today because I'm sure that Martin will do this, and my focus today is the connection with the inspection paradox. What I do want to emphasize here are two things. First, see that the only way that this thing could diverge is by r being 0, but if you're resetting at some finite r, not 0, then r is not 0, or by this guy, the Laplace transform being 0, but the Laplace transform is not 0, and unless t, this first passage time, is always infinity. Basically, you're looking at a process that never completes. So this guy is finite. It does not diverge. So this means that if you start with some first passage process that has an infinite mean and you add resetting, you'll get a finite mean. So all these class of processes that have an infinite mean first passage time with resetting, you regularize them, which is, I think, quite amazing. But now the question is, what happens for first passage processes with a finite mean? And also, you know, from the very basic intuition of why does resetting works when it works? This is something that we want to understand. And without a proper interpretation of this formula or something else, you will not get it. So this is where I'm aiming. I want to show you now that, in fact, the inspection paradox and the resetting paradox are one and the same, in the sense that it is exactly these situations that you wait for the bus longer than you anticipated. These are exactly the cases where resetting also helps you lower the mean completion time of a process or the mean first passage time. So how are we going to do this? I want to think for concreteness about some first passage time process, but the argument is completely generic, okay? So I have some diffusion here, okay, and I have a target, and I'm putting a reflecting boundary so as to regularize the mean, and this is fluctuating, and I'm looking at the time that it hits the target, and when this happens, I start a new first passage process and so on and so forth, like bus arrivals one after the other. And I want to think about the effect of resetting here. So I'm going to do this perturbatively. I want to look at a very long observation time. And let's think about what happens when I turn on a small resetting rate r. What is small? Small such that r times the observation time is much smaller than 1. So what's the most likely thing that would happen? Nothing, right? Because the resetting rate is small, so the most likely thing that would happen during the observation time is nothing, no resetting. But I want to think about the first order correction to that. So if a single resetting event occurred, where did it occur? Along the observation time. This is what I want to answer now. So let me split my observation time 3 ways. A1, B, and A2, 3 different chunks, okay? And I want to ask, what is the probability that resetting occurs in this interval B, given that a single resetting event occurs along the observation time? So this is just the probability to have 0 resetting events in A1, 1 in B, and 0 in A2, and I need to normalize by the probability to have a single resetting event throughout because I'm conditioning. How am I going to do this? Well, resetting occurs at a constant rate, so the number of resetting events is just taken from the Poisson distribution because this is a Poisson process. So I'm going to plug in. So this is the probability to have n events in the observation time, but it's also true to this guy and this guy and this guy because they're disjoint. So I'm just going to plug in this probability of having 0 here, 1 here, 0 here, and then the probability to have 1 throughout the observation time, cancel whatever I can cancel, and what you get is just B over T obs. This means that the probability that you will have resetting in this interval is just proportional to its length. What does it mean? Because these intervals are arbitrary, you can shrink them and move them and do whatever you want with them. It means that resetting occurs uniformly across the observation time, okay? So there's a uniform distribution. If there's a uniform distribution, this means that you're visiting the system at some random time uniformly, like the passenger that arrives at the bus stop. So this is the same statistics. There's the same statistics for resetting as random inspection of the system. And this is what allows us to borrow insights from the inspection paradox. So now imagine what happens, right? I have this first passage time process, okay? And I turn on a small resetting rate. And a resetting occurs somewhere along the way. And then I ask myself the following thing. If I arrived here, okay, how much time will it take my process to complete? Well, this is just the residual time to complete. If I reset, how much time it will take me to complete? Well, if I reset, then I start fresh. Then I draw a new time from the original first passage time distribution. So in what situations will resetting expedite completion? In these situations where the mean completion time after resetting, okay, which comes from the original distribution, is smaller than the mean of the residual. Basically, when you're trading long completion times on average with shorter completion times on average. And we have an expression for this mean of the residual. Now we can cancel this t and this t from both sides. And what you get from this is that resetting is guaranteed to expedite completion of any first passage time process that has a CV, a coefficient of variation, that is larger than 1. So in any first passage time distribution where the standard deviation is larger than the mean, applying resetting, a small resetting rate, is guaranteed to lower the mean first passage time, just because of the inspection paradox. This is fundamentally why resetting works. And there are explanations for why resetting works that are tailored for specific systems, but this explanation actually captures the essence, I believe, in the most general sense. I want to show you how this bears on a certain type of universality that we've discovered with regard to processes that are being reset at an optimal rate. So one thing that appeared in the original paper by Martin and Satya is a plot of this kind, where you basically plot the mean first passage time with resetting as a function of the resetting rate. And here I plotted it for different ratios of d over L squared. L squared over d is just the diffusive time scale here. And what you see is that for low resetting rate, it diverges. We know R equals 0, you get an infinite mean first passage time. Where it's very high, it's also large, but in between there's an optimal resetting rate, okay? So this optimal resetting rate was shown to be inversely proportional to this time scale. But you can ask, what happens at this optimum, okay? So if I think about it, okay, so I have here a minimum of the mean first passage time, but some trajectories will end faster, some trajectories will end sooner, okay? Faster, some will be slower. So I can look at the standard deviation in the first passage time over the mean first passage time with resetting. So this is just the CV of the first passage time of the reset process as a function of the resetting rate, here normalized by the optimal resetting rate. And if you do this for all these curves, they fall into a single master curve. And what you see is that the CV of the process with resetting at the optimal resetting rate is exactly 1. Why is this interesting? It's interesting because this result is true not only for diffusion, it's actually true for any first passage time process that you restart at an optimal rate. So if you pick the resetting rate such that you have a minimum or actually a maximum of the first passage time distribution, the CV is going to be, at optimality, is going to be exactly 1. Why is this? We can understand this quite easily now with the aid of the inspection paradox. So what I told you before is that, you know, if you look at the system, this is the resetting rate, let's look at 0, okay? System with no resetting. if you see that the standard deviation in the first passage time is larger than the mean, introducing a small resetting rate will lower the mean, okay? But so this works for an infinitesimally small resetting rate. But it turns out that it also works for higher resetting rates. Why? Because if you see here that you reset at some rate, and still the standard deviation of the reset first passage time process is larger than the mean of the reset first passage time process, then the entire thing, okay, has a CV that is larger than 1. So this means that if you will introduce a small resetting rate and reset the entire black box, you will lower the mean even further. But resetting a process that has already been reset with a rate R with an additional rate delta is like resetting the original process with a rate R plus delta. And so the mean first passage time will continue to go down and down and down and down, and as long as the CV, as the standard deviation is above or higher than the mean. And then exactly at the optimum, exactly when the mean first passage time has a minimum, these two curves will cross. Why? Because otherwise you'll get a contradiction to this being a minimum. If the standard deviation will be higher, then increasing the rate further will take you further down. If it's lower, then it should take you up. So this will be a contradiction to the fact that here the derivative should be 0. And so this result holds at optimality for any first passage time process, and it was demonstrated now on a bunch of different systems. Yes? So that's a great question. Is the Poisson way of resetting the optimal way of resetting? We actually know that it's not. There is an optimal strategy for resetting. This optimal strategy for resetting, and this is something that we proved, is sharp resetting. You want to wait a fixed amount of time and then reset. What is this amount of time is non-universal, but this is the strategy that cannot be beat. If you tune this waiting time correctly, you will not be able to beat this strategy in any other way. It's not included in my talk today, but there is an optimal strategy. It's well characterized. It's the simplest strategy that you can think of. Just restart at constant time intervals. Okay. In the time that I have left, I want to say a few words on some recent developments. So up until this point in the talk, I implicitly assumed that resetting takes 0 time. Basically, you teleport your particle back to the origin with 0 time cost. However, this in realistic scenarios is really not true. And you want to think about a situation where you have overheads, time overheads. So some ongoing first passage process, and you want to restart it, but then there's an overhead time before you can start the process again. You need to wait. There's some delay, and only then you can come back. Why is it interesting to think about these kinds of systems? Because restart with time overheads is exactly equivalent to a change of labels to what people call the Michaelis-Menten reaction scheme that describes enzymatic catalysis, but also many other things in the cell. Catalysis, so here you have an enzyme that binds and unbinds a substrate, and when they're bound, you can get a product by the process of catalysis, and you can think about this process maybe as barrier crossing, but it could be much more complicated than that. In general, you can think about it as a first passage process. There is unbinding, which is restart de facto. And then if you want to start the catalytic process again, you need to bind, and binding takes time. It takes time for a molecule to rebind your enzyme. So you want to think about these time overheads. They're important. And the question is, how do you do it? So you can do it the hard way, like we did in these papers, or you can do it in a much easier way and at least get some insight regarding the problem. You can't get everything, but some insight you can get if you appeal again to this notion of the inspection paradox. So if you resetting occurs or unbinding occurs at some random time, you can ask, how much time does it take my process to complete without this resetting? This is just the residual time. But if I reset, then I need to pay an overhead, and then a new fresh completion time. So now I am comparing this residual time with the overhead and the mean of the completion time, the mean of the first passage time. And despite the penalty, we see that resetting will expedite completion, and I'll get more product per unit time, say in this example, when the mean of the residual is larger than the mean times this penalty that is associated with binding, the average time it takes you to bind. And you can rearrange this and write it again in terms of the CV. So now the CV needs to be larger than 1 plus twice the mean of the overhead, the mean of the binding time over the mean of the catalysis time. But you see here that if fluctuations in the catalysis time are large enough, despite the penalty, resetting will still help you. Another reason to consider these overheads comes from, yes? Yeah, so this is perfect. So here in this model, there are no correlations between this delay time is completely agnostic to what happened before, which is well expected, and it's a good model for how enzymes work. But, and this is now my next slide, if you think about diffusion with resetting, right? But realistically, you think about it. And these are experiments that were done in the lab of Yael Roichman. So you heard about one set of experiments that was done. There was also another set of experiments that Yael did in her lab. And what you see here is a particle diffusing, a colloidal particle diffusing. And from time to time, you come with optical tweezers, you grab this particle, and you bring it back to the origin. And what you can appreciate here, I think, is that there is some sort of a space-time coupling, right? Because if I reset from far away, it takes me longer to get to the origin than if I do it from close by. So this overhead time is space-time coupled, and you want to think about how to include that into your theories, at least if you want to think about realistic scenarios. And another reason to do this is this fable of the butterfly and the bee. So the butterfly looks for a target indefinitely until it finds it without resting. The bee does something else. It searches, but if it doesn't find the target, it will return back to the hive. And returning from far away will probably take more time than returning from close by. And so you have space-time coupled return times, penalties that you have to consider. And also waiting times at the hive that could come from some generic distribution, or could be zero if you want to neglect them. But there is a different kind of delay here that one would like to account for. And it turns out that you don't need to assume anything about the way that this search process goes on, the distribution of the targets, and so on and so forth. The challenge was to analyze this in complete generality. And what you can show is that search with home returns, the way the bee searches, is going to be better and provide an advantage under conditions of high uncertainty. So in any situation where the first passage time without resetting has a CV that is squared, that is larger than 1, and now plus 2 types of penalties, one that is not space-time coupled, that just come from generic waiting times, and then another one that is space-time coupled, and here you have the mean of this return time. Whenever this occurs, when you have large fluctuations, coming back home will be beneficial despite the penalties. Yes, sure. So in the 5 minutes that I have left, I want to comment about steady states and non-equilibrium steady states of systems with stochastic resetting, and show you that we can also understand these systems with the aid of the inspection paradox. So where is this question coming from? Again, I think it can be traced back to this paper of diffusion with stochastic resetting. So you can ask, when will a particle reach the origin? But you can also forget about any targets or things like that, and just let the system evolve and ask, where will the particle be if you wait long enough? okay? So what is the steady state that this system attains? And it's going to be a non-equilibrium steady state because you're taking the particle and you're resetting, so there are currents. You want to understand this steady state. How can you do this? Well, let's think about it in the following way. So for concreteness, let's think about diffusion, but in a second I'll show you that it works in general. So you have a particle that is diffusing and you're resetting it. And these are the resetting time intervals, R1, R2, R3. If you're resetting at a constant rate, they come from an exponential distribution, but in general, you can pick them from an arbitrary distribution. And these are now exactly like the times between bus arrivals. So now the resetting times, I'm going to draw parallel between them and the times between bus arrivals. And what do? So the system evolves, and you come at some random time after it evolved for a long time, and you watch it, and what you see is the steady state. But what do you see? So basically, you come at a random time. You come after some resetting event has occurred, and here there was free propagation during this time t-insp, the inspection time. And what you see is what you see at this random inspection time. So previously we were looking forward in time. This inspection time is looking backward to the previous event that occurred, but they have the same statistics by symmetry. So the inspection time is going to have the same statistics as the residual time, and the mean of this time is going to be just the second moment of the resetting time distribution over twice the first moment, and you can also write it like that in terms of the CV. Now, if you take diffusion, that has a mean square displacement that is 2dt in the absence of resetting, and you apply resetting, what happens to the MSD? Well, you need to take this MSD and just average it with respect to this inspection time. And when you do that, this is what you get. D times the mean of the inspection time, but then you see that you're sensitive to fluctuations in the resetting time. You can generalize this and get the entire steady state distribution. How? For this, you need to know what the system is doing in the absence of resetting. So let's say that the probability to find the particle at position x at time t is known. For diffusion, it's a Gaussian. For other systems, it is what it is. It can be a multi-body system with interactions, with whatever you want. But assume that you know the time evolution. Then what happens? If you want to know the steady state with resetting, all you need to do is take this probability and average it with respect to the inspection time. So this is this integral right here, and it turns out that this exactly is the density of this random variable, the inspection time. Why is it? Because if you want to have an inspection time t, then you have to fall on an interval that is longer than t, and so only intervals of length L that are t and larger will contribute to this average. If you fell in such an interval, observing something is just 1 over the length of the interval because you can fall everywhere. This is where the 1 over L comes from. And then what is the probability that you landed inside such an interval? This is just the frequency at which these intervals occur, but times L because you're biased towards longer intervals. And so the L and the L cancels out, and this is why you get this probability. It's not normalized, so this is just a proportionality. So you normalize by whatever it is you need to normalize, and it turns out to be exactly the mean of the resetting time. And this is the formula that you get. In the special case where you have resetting at a constant rate, this boils down to be the R, the resetting rate, times the Laplace transform of the propagator in the absence of resetting. And I'm sure that Martin will elaborate on this formula and how you can get it via the renewal method. Okay, so I'm done. I just want to summarize. I had no new results today, just a fresh perspective on existing results on resetting systems. I showed you that we can understand a lot via this lens of the inspection paradox. And this paper was written such that a second-year student in physics, math, chemistry can pick it up, read, and understand Nothing complicated about the math over there, really simple stuff. So it can be used as an introduction to stochastic resetting. I would again like to thank the people who did the work. Apologize for not having been able to cite all the relevant papers on stochastic resetting. There are many papers now. I admittedly focused on our work, and I didn't even get a chance to cite all the relevant papers that are there. There is an excellent review by Gregory, Martin, and Satya, also called Stochastic Resetting and Applications, that I invite you all to look into. And with this, I would like to end. Thank you. Thank the funding agencies, past and current members of my group. And if there are any questions, I'll be happy to take them.